This is the answers portion of the video lesson 1 of the course Real Analysis. Question 1. In the first question we have 4 sets, each of which is a solution set of an equation. To find the extensional definition of each we must solve the equation. Part A. This is a linear equation with the only solution being 2.5. Part B. Subtract 5 from both sides to get 3 to the x equals 81. Take the logarithm of both sides with base 3 to obtain x equals 4. Part C. The left-hand side is a factorized polynomial of degree 4. This is sometimes referred to as a quartic equation. To solve the equation, remember that if a product is equal to 0, then one or more of the factors must equal 0. The equation is solved when x equals minus 4, 3, minus 2, or minus 5. Part D. This equation has no solution, as given a right-angled triangle whose hypotenuse is fixed as 1, there is no combination of angles such that the shorter sides have length 2. Question 2. Part A. First, we state the logical definition of the subset relation. Then, we replace a subset with the empty set. Recall that a statement is a tautology if it is true no matter what the truth values of the substatements are. For example, tomorrow it will rain or it will not rain. If we can prove that the statement on the right is a tautology, in other words, that it is always true, then we have proved that the statement on the left is always true. One consequence of the definition of the empty set was that this substatement is always false. The truth value of the substatement on the right can vary. But this doesn't matter, as an implication is always true if the antecedent, the substatement on the left, is false. So the statement has been proven. Question 2. Part B. This set is a singleton as it contains one element, namely the empty set. Question 2. Part C. This set is not a doubleton as it contains only one element. Question 3. Part A. The power set of the set comprised of A, B, and C is this set containing 8 elements. Notice how we included the empty set and the set itself, and how we listed the elements in a logical fashion. Part B. We stated that we would adopt the convention that a proper subset of a set X would be any subset that was neither the set X nor the empty set. Therefore, the answer is a doubleton comprised of X and the empty set. Part C. You may have drawn a diagram similar to this. We drew it in such a way that if you head downwards from a set, you will always find subsets, and if you head upwards, you will always find supersets. If you found this exercise interesting, investigate Hasse diagrams. Question 4. Part A. The answers here are just a product of practice. If you made an error, check the definitions of the operations and try again, or try with simpler sets first. Question 4. Part B. Notice how the Cartesian product of any set with the empty set is the empty set, as a consequence of the definition that one of the members of the ordered pair must belong to the empty set, but we know that this can never be the case. Question 4. Part C. Again, this was done for the benefits of getting used to the notation. Question 5. Set intersection is a commutative operation. We can prove this by looking at the predicate in the intensional definition and seeing that by definition, logical conjunction is commutative. Set union is also a commutative operation. We prove this by the same method. Set difference is not commutative. We only need a single counterexample to demonstrate this. You may have thought of your own counterexample. Remember, it is best to provide the simplest counterexample possible. Both the relative and absolute complement operations aren't commutative either, as if the arguments are swapped, it is only defined if they are equal sets. The Cartesian product is not commutative, as demonstrated by this counterexample. Question 6, Part A. The universal set is probably the integers, symbolized by a z, so the complement is the odd integers. Question 6, Part B. The universal set is probably the real numbers, so the complement is a set of all x, such that 3x squared is not equal to 7. We will define the real numbers more rigorously in the forthcoming lessons. Question 6, Part C. The universal set is probably the lowercase Greek letters, so the absolute complement is a set comprised of the 21 letters not listed. The Greek letters are often used in mathematics, mainly because the English letters are reserved for other things. Question 7. This question was quite abstract, and it is not essential you are able to answer it at this stage. We can use a result from question 4b and state that the equation holds if A is the empty set or if both A and B are the empty set. Now supposing that neither A nor B are the empty set, for the equation to hold, the element x belonging to A implies that all ordered pairs xy, where y is an element of B, belong to A as well. They are all distinct from x. But then, these ordered pairs being elements of A imply even more distinct ordered pairs belong to A. It can be seen that A is an infinite set. Your argument may have been similar to this. In a future lesson, we will return to this question with more rigor. Question 8. Set union and intersection are associative by arguments similar to question 5. We simply need to look at the predicates in their intensional definitions and see how they are logically equivalent. The Cartesian product is not associative, as we can see by this counterexample shown here. If, for two operations, we have that the following is the case, then we say that one of the operations is distributive over the other. For example, multiplication is distributive over addition. Be aware though that the converse is not always true, as addition is not distributive over multiplication. Question 9, Part A. In this question, we are establishing that set intersection is distributive over set union. We first look at the intensional definition of the left-hand side, and note that logical conjunction is distributive over logical disjunction, so we can replace the predicate with a logically equivalent predicate. Finally, we recognize that this is the intensional definition of the right-hand side. This completes the proof. It is conventional in mathematics to end proofs with a small solid black rectangle. Question 9, Part B. This statement is true as well. We adopt the same strategy. We look at the intensional definition of the left-hand side, use the distributive law of conjunction over disjunction, and rewrite the predicate. Finally, we recognize that this is the intensional definition of the right-hand side, completing the proof.